All right, let's continue the adventure going through the calculator multiple choice section of this 2014 released exam. Number 82, it says the figure above shows the graph of f prime. Okay, so that's the derivative of f. All right, from -6 to 8. So 1, 2, 3. Let's make sure we've got these labeled just so we're certain. There's 8. And then -6 is right here. Okay, so we're good. Of the following, which best describes the graph of f? Now remember, this is f prime, f prime. So we're looking for mins and maxes on f. Well, what happens there? Isn't that first derivative is either undefined or 0? So we have some opportunities where, just maybe, we have a max or min. Now, does that change sign there? Yes, it sure does. So f is increasing up to here because that graph is above the x-axis, right? And then f is decreasing here. Well, what do you know? That would be a max right there. Now, the first derivative that we're looking at is 0 here, but it does not cross through the x-axis. It doesn't change sign. So the function f is still decreasing here, but then look right here. It does change to, f changes to increasing again. So we're decreasing and then increasing right here. I didn't draw that very well, but you get the idea. That would be a min. All right, so we've got one max and one min. So we're down to either A or B. Which is it? So the next part of this is inflection points. How do we find inflection points? Inflection points come from when that second derivative is either 0 or undefined. And I'm looking at this, it happens at 3 places, it looks like. Definitely here, definitely here. I think it looks like it goes horizontal here. But remember, the second derivative involves slopes. So right here, the second derivative is negative, and over here it still is. So did we change concavity at -4? No, we didn't. Because the slopes are still negative, the slopes represent the second derivative because we're looking at the first derivative. All right, so let's keep going. Here let me use my highlighter a little bit more exaggerated. Right here, we have a negative slope and we do change to a positive slope. So all of a sudden, the second derivative has crossed through the x-axis. It's now positive. So that would be an inflection point right there. And same thing here. You see how we end up going, we're negative and then we're positive again. I forgot to label one right here. We have another horizontal tangent right there, right? And indeed, it does change from positive to negative. So we have an inflection point here. We have, this is becoming a mess. Hopefully you're following me here. We have an inflection point here, here, and here. And it's because the slopes have changed signs at those horizontal tangents. So the answer is A. The answer is A. It's not 4. Some students would say 4 because of this horizontal tangent here, but this was not an inflection point. Hopefully that all made sense. Moving on to number 83. Let f and g be continuous, and then they're giving the values of integrals. So we're going to, you know what we're going to do. We're going to use the properties of integrals to solve this out. So they want to know what this integral would be. So it looks like we're going to need to figure out this and then subtract 3 times the same bounds on g. Does that make sense? Now, 0 to 3 on g, let's start there. They gave us 3 to 0. So what is this equal? This would be positive 7. Because the bounds are reversed, you just change it to positive. Now let's back up. 0 to 3. Well, this is 0 to 6. This is 3 to 6. So wouldn't 0 to 3 be the whole thing minus the part? Gives you the other part. So this would be 9. That's the whole thing. Minus the other part gives you the 0 to 3 part. And we also need the half out front. Notice I haven't used a calculator at all. In fact, I still don't need it because 1/2 times 4 is just 2. Minus 21 is negative 19. And negative 19 is the answer. See how easy that one was? That was, whenever you get to a question, it's not a bad idea to take a half of a second and think, what is being tested here? This was just properties of limits and how you can manipulate those bounds. All right. 84. 84, here we go. The regions A, B, and C are defined here, and the areas are 14, 16. Now notice that's under the x-axis, so I'm thinking, oh, that's going to be negative. And then C is 50, 50. What is the average value of f on the interval 0 to 8? Now, average value is where you take the integral on the function, not the absolute value of the function, just the function, and you divide by b minus a. So this would be 1 over 8 minus 0, of course, right? What about the value of the integral? All we have to do is add up the areas, but don't forget the 16 is negative. So it would be 14 plus negative 16 plus 50. So that's 1 over 8 times. You can do that in your head without a calculator. Do it. I bet you'll do it more quickly. 48. And look at that. 48 divided by 8 is 6. And that is the correct answer there on 84 is A. We haven't used the calculator this entire video. Now in this next one, I believe we do. And you can see the answers are decimals. So let me bring the calculator back for you. There it is. So we got it all queued up and ready to go. A particle moves along an x-axis, left and right, possibly, according to this velocity function. So don't forget, it could go left and right, right? What is the total distance traveled? So sometimes velocity could be positive. Sometimes it could be negative. So we don't want to just integrate on the velocity function. That's called displacement. What I've got written there would be displacement. What do I have to do to get total distance? I have to flip the entire graph up over the x-axis so it's always positive all the time, and then I can add up all those rectangles, right? That's what integrals do. Those Riemann sums that you spent so long doing. All right, so we go to the calculator on this. Math, number 9. The integration from 0 to 2. Oops, 0 to 2. And the function is a fraction. Now, I do need to do the absolute value. Now, that's under math. And you go over to num. And number 1 there is ABS. Right? And then I'm going to put a fraction in here. So I do have to put the top inside parentheses. Oops, and it didn't work, did it? Yeah, it did. Okay. X squared minus 1. Now I'm going to close my parentheses and divide by, I have to open another parenthesis, x squared plus 1. X squared plus 1. I close my parenthesis. I change this to a dx problem. And I think I'm ready to hit go on this. And let's see what the answer is. 0.927. All right, and I'm looking at the key, and what do you know? We got it right. All right, so that was a calculator question. The absolute value was really important there because of the magic word total distance traveled. We needed to flip the entire graph up above the x-axis. All right, let's do these two, and then that'll be the end of this video, and then I'll finish it out on the next video, which will be linked in the playlist. Line L is tangent to the graph of e to the x. Okay, So you know what e to the x looks like, right? It looks like this. This is y equals e to the x. So we're at k, we are at e to the k, wherever the heck that point is. All right, you with me so far? What is the positive value of k for which the y-intercept of the tangent line is 1/2? Well, what I'm starting to think about here is y equals mx plus b. And since it goes through 1/2, I know the y-intercept is 1/2, right, on the y-axis. Now, how do we get slope of a tangent? That's just the derivative. And y prime would be also e to the x. So y prime at k, the slope at k is what? E to the k. All right, so what do we have so far? We have y equals e to the k x plus 1/2. Now the point, remember the point was k e to the k. That's your x and y that we're going to go ahead and plug in. So let me zoom in a little bit here for you so you can see better. So this would be e to the k over there equals e to the k times k plus 1/2. Now, personally, I would do just a pinch of algebra at this point, but you could go to your calculator and type this in as y1 and this is y2 and find where they hit, where they equal. But before I do that, I'm just going to change it a little bit because I think it might save me a little more time. So e to the k minus e to the k times k equals 1/2. I then factor out an e to the k, and I get 1 minus k equals 1/2. At some point you may be holding out, I know when I was previewing this problem earlier, I was holding out hope that I might be able to solve for k, but you cannot here. E to the k equals 1 over 2 to the quantity 1 minus k. At least you can't easily solve for it, I guess I should say. So I want to put these into the calculator. All right, so we're going to go to our graph. I haven't done any graphing yet in this, so I'm going to type e to the x. This problem takes a little longer simply because of all the data entry here. 1 divided by the quantity 2 times, I'm going to do another quantity, 1 minus k, but I have to use x, of course. All right, and then graph it. Let's see what we've got. All right, so there's my e to the x. Here comes my other one, and you can see there it does hit it. So let me just zoom in here a pinch. I'll hit enter. Let's redraw it. All right, so I would really love to find this point right here. Wouldn't that be great? So how do we do that? We do use the intersect feature. Okay, so we do second, calculate, which is above the trace button. You guys probably know all this, but I'm just trying to talk you through it. 5 is the intersect feature, and then it says, okay, I need to know the two functions. So the first function is the blue one, second one is the red one, and now I'm going to scroll. Oops. I'm now going to scroll. Let me clear this out. Let me try this again. Second, calculate. 5. Enter, enter. And I was hitting the wrong button for scrolling. So I'm going to get myself a little closer because it actually hits twice. So you do have to get closer to this one than the other one. I'm now going to hit enter. And I see the intersection happens at x equals 0.768. 0.768. And number 86 is indeed 0.768. So there you go. That was the answer there. So hopefully you followed all that. Again, we could have put it in at this point. Probably wouldn't have been any harder, honestly. But I just decided to do it that way because I'm an algebra teacher, so I like to do a little bit of algebra because I think I was holding out hope that I could solve for k and actually get an expression rather than doing this graphically. But I think graphically was the way to go. All right, moving on. A differentiable function f, so that means the derivative exists everywhere. There's no corners or cusps or crazy things happening on this thing, has the property that the slopes are always under or equal to 3. That's what, when I'm thinking about this, I'm thinking the rate of change or the slopes are all under, let me write that down. The slopes are all under 3 between 1 and 8. Okay, so let's do 1 here and 8 over here. Now, f of 5, which would be right here, is 6. That's a given. Which of the following could be true? Now remember, this thing has slopes that are up 3 over 1 at the most. Let me say that again. Slopes on this 3, the slopes on this function are always 3 or less. It can't be steeper than up 3 over 1 at any point in time. Hopefully that makes sense. So, could we possibly start f of 2, could that be 0? I'm sorry, at 2, could we start here? Well, sure, if we go up 3 over 1, up 3 over 1, I'm well above that, so I could certainly go at a lower rate than 3 and get there. So, yes, that one's possible. All right, let me get this mess out of the way. Now, if f of 6 is 2, is that possible? That's an easy one because the slopes are allowed to be negative. This does not say the slopes are always positive. So yes, we could be here and then we could go down here with a negative slope. So that one's possible also. All right, so what about f of 7 being 13? Way the heck up here at 13. F of 7. Could that be 13? Well, if we start here at 6 and we go up 3 over 1, we're now at 6, 9. And then if we go up 3, which again is the maximum rate that we can do, and then that would put us at 9, and then we would be at 12. Right? We went up 3, I'm sorry, this is at 7. Up 3 over 1. So could we ever have gotten to this point up top? Nope, because this was the fastest rate we could have ever gone. And that last point is above that. So the answer is 1 and 2 only. So this was a problem testing your understanding that first derivative represents slopes. So your curve can slope at a max of up 3 over 1. That's the best you can do at any given point. So that last one, Roman numeral 3, was above the trajectory. That was our maximum. All right, I'll continue with number 88 all the way to the end on the next video. All right, hopefully this is helping you.